Hi. The concept of derivative originates from the problem of defining the tangent line to a plane curve. To clarify ideas, let us consider a curve defined as the graph of a function, y function of x, and observe its graph near one of its points, let's say x star f of x star. Ideally, the tangent line to the graph is a line passing through the point and not intersecting the graph at other points, at least near the point x star f of x star. But how can we determine such a line? The goal of this video is to answer this question. Now, through point x star f x star, infinitely many lines pass. Excluding the vertical line of equation x equal x star, all other lines have a representation of type y equal mx plus q. Now, since all these lines pass through the point x star fx star, by imposing the passage condition, we get that fx star must be equal to mx star plus q. This allows to express q and to simplify the equation for the straight line as follows: y equal mx minus x star plus fx star. This form emphasizes well the passage condition, because when x equal x star, this term is 0, and then you get y equal fx star. So this form also emphasizes that to know the tangent line, we just need to know what is the angular coefficient of that line. Since a single point cannot uniquely determine a line, we need a second point of passage. So let us consider a second point on the graph with an abscissa different from the first one, so from x star. We take a point like x star plus h, where h represents the displacement from the point x star. We will have h different from 0 to ensure that this is really a second point. Now, through these 2 points, x star fx star and x star plus h f of x star plus h, passes just a unique line with this equation and with the angular coefficient that can be easily determined. In fact, we do the ratio between the variation of ordinate over the variation of abscissas, and we get this. This quantity is called incremental ratio because it is a ratio of increments, increment of f over increment of the variable x. Now, by varying h, it becomes, as h becomes smaller, the second line tends to rotate, approaching a limit position. Ideally, as h goes to 0, the 2 points, the 2 passage points, tend to coincide, generating a line that in principle should pass only through the point x star f of x star, or at least near it. Since we cannot take h equals 0 in this formula, we are naturally led to consider the limit for h going to 0. So we define this limit, and this should be the angular coefficient of the straight line we are looking for. This led to the following important definition. So let f be a function of real variable defined on a domain D, the real line, a point x star in the domain, which is in the interior of the domain, that is, for which there is a neighborhood of the point entirely included in the domain. We say that the function f is differentiable at point x star if there exists a limit of incremental ratio and the limit is finite. We call the limit the derivative of f at point x star, and we denote the derivative by f prime. This is the Lagrange notation. Other notations are diffused like f dot, which is the Newton notation, and df over dx, which is the Leibniz notation. By previous discussion, we also define the tangent line at point x star as the line of equation y equal f prime x star times x minus x star plus f of x star. Now, we do not have many examples to test this concept. However, there is one which is particularly easy. If the function f is affine, this means that the graph is exactly a line. It is natural to expect that a tangent line exists and it coincides with the function itself. Indeed, we can suspect that the angular coefficient of the tangent will be the same of the function, so f prime of x star be equal to m, whatever is x star in R. This can be easily proved because if we compute the limit of the incremental ratio, in this case, the calculation is really straightforward and elementary. So we replace the values of the function here in the increment at the numerator, divide by h, then we simplify whatever we can, and we end to this limit for h going to 0 of mh over h, which is clearly equal to h. Now, we define the tangent line by definition saying that that straight line is the tangent line. But a natural question is, in which sense is really tangent this line to the graph of the function? Instead of thinking in terms of intersections between the line and the graph, which would be difficult to verify, we introduce the gap between function and a generic straight line passing through that point, non-vertical. So this is the quantity delta x, which represents the distance between the quote on the graph and the quote on the straight line, so which is defined as f of x minus the quote on the straight line. Now here something interesting happens. If we compare this quantity delta x to the basic quantity going to 0 at point x star, which is x minus x star, and we do calculations, we see that this is exactly equal f of x minus f of x star divided by x minus x star minus m. Now here you should recognize that there is the incremental ratio. In fact, if you call h this increment, here you have exactly x star plus h. Therefore, if the function f is differentiable and we send x to x star, this goes to f prime x star minus m. And this leads to two important conclusions. First, if the straight line is not the tangent line, then delta x, the gap between function and straight line, goes to 0 proportionally to the increment of the variable, so x minus x star. While if the straight line is the tangent, then the delta x goes to 0 faster than x minus x star, because this difference will be 0 now. And therefore, this means that this ratio goes to 0. This meaning that delta x is little o of x minus x star. So the tangent line has something special. It makes the gap between the tangent function and the tangent line the smallest possible, a little o of the increment x minus x star. This has also another nice interpretation. If we remind that delta x is little o of x minus x star, and this is the definition of delta x for the case when the angular coefficient is that one of the tangent, then we can see that the function must be equal to a first degree polynomial, which is called the Taylor polynomial, plus a little correction, which is little order of this term. So which can be considered negligible with respect to the polynomial. This formula is called the first order Taylor formula. And on this formula is based the numerical calculation of a function. Well, that's it. So it's now your time, and I would suggest you to take more confidence with the definition of differentiable function, derivative, for example, solving an exercise of this type. And if you want to work still on the definition, but at a more abstract level, you should also consider this problem. Well, good luck and nice study.